Hi, everyone. Let's wait for a couple of minutes. I see the participant count is increasing. Okay, I think we are ready to start. So, welcome to the GPU programming course organized by Turkey National HPC Competence Center. So today, in the first day, I will first talk about parallel programming, high performance computing, parallel computing. What do we do here? How do we do it? And then I will talk about CUDA. So in the first session, we will be, I think, ready to, after the first session, we will be ready to write some hello world in CUDA. And in the next session, I will talk about GPU memory hierarchy, how to improve data locality and CUDA streams, which will allow you to submit multiple things, multiple tasks, jobs to a single GPU and overlap multiple computations, communication and computation. So let's start here. Okay. So computing is, well, I mean, it started around it started before, in fact. So we have Charles Babbage, Ada Lovelace. So we have many famous people who built the foundations of computing. Then we foresaw the word computer in an ad. Computers are wanted. So back then, the term computer was being used for the people, for the women especially, who are doing computing, mathematical calculations, in fact. Then we have Alan Turing. So what can we compute? What can't we compute? What can't we find? What can't we find? So he looked for answers for these questions. Then there was World War II, and the technology improved significantly. So we have in 1943, we had Colossus, this computer, and 1945, ENIAC. And after that, there were people, and we have also ABC, Atanasoff Berry computer. So the first, it is said to be the first electronical computer applying like binary representation and some other modern ideas that we have. Now we can compute. So we have these computers, and what we want to do is high performance computing. There is no low performance computing. You don't want to have low performance. So what you want to do always is, in fact, utilizing the computational power of your device, of your processing unit, of your memory subsystem, etc., etc. So, but today, high performance computing refers to systems that can rapidly solve difficult computational problems. The HPC, so this is how we say it, the HPC clusters today, they contain significant processing capability, like millions of cores and petabytes of storage capacity easily. And they are being used for diverse range of scientific, engineering, and business fields. I like the saying that HPC is like a telescope, because with it, you can understand things that you previously that you could understand with by building things. Okay, so without building, for instance, wings for your plane, you can understand that if they are efficient, if they will make your plane better, if its fuel usage is optimized, etc., etc., by using HPC. So they say telescope because with telescope, you don't go to space, you are not physically in the space, but you can see the stars, you can observe them, etc., etc. So HPC is like a telescope for many scientific, engineering, and business fields. So I talked about the history, and one important historical thing which we still feel its impact is the von Neumann architecture. Well, the ideas back then, the ideas were around, so he wasn't the proposer of this design, or I mean, solely, but still he had this in one of his reports, and what he says and what back then what people were thinking is this central processing unit. So we have multiple components. I will talk about them briefly. And then there is a memory unit here. So they need to communicate through some channel, bus. So the data is coming from some device, and then we store it in the memory. And then when you want to do something on it, you need to bring it to the CPU. So that's the first thing that you can observe from this design. And after that, once you are done with it, you present the result to the user by using an output device. So this thing here is really important, this bus, and we will talk about why. So the conventional architectures, as I just talked about, they contain processor, memory subsystem, memory system, and the data path. So each of these components present significant performance bottlenecks. There are various applications that we use, that we do on computers, right? And each of these applications has their own characteristics to utilize these components of the conventional architectures that we have. So one of them may be requiring small amount of data, but performing a huge amount of floating point operations, flops, or performing huge amount of computation on the small amount of data. So you use the processor part of the architecture significantly. And if one application brings, maybe you are looking for a word inside gigabytes of data, terabytes, petabytes of data. So you just look to a data and then you say, okay, this is not the word that I am looking for. Maybe you are counting some specific words, okay, the number of some specific words. So if you use a huge amount of data, but do less computing, then you are utilizing, and you are in fact bounded the performance of the memory system. So we have different characteristics for applications, okay? So the computer, so these control and data paths, so let's talk about them a little bit. So computer is processor plus memory system, and processor is control plus data path. And control can be considered as a finite state machine. Don't get confused. This is just, you do something, so it goes to another state, you give another input, it goes to another state. So it just changes states based on inputs. And the input is the instructions and data path conditions, the current data path, the current state, in fact. So you, to find the next state, you find you need the current state, right? And the outputs of this is the control signals and the operation codes for the data path. So data path contains all the functional units, registers, buses. So the physical components that you transfer the data, that you process the data, process the instructions. So this part is data path, and it is controlled by the control component. And the control component will be important for CUDA when we try to describe single instruction, multiple threads, or single instruction, multiple data paradigms. Okay, so we had Moore's law. He said that semiconductor complexity would continue to double annually until about 1980, after which it will decrease to a rate of doubling approximately every 2 years. And he was right, because, I mean, we see the impact of this, and also other rules like the Dennard scaling and other rules, which yield multiple cores, having multiple cores on a single CPU socket instead of a single core having a huge amount of power, like with high frequency, very high frequency, okay? So like maybe 100 gigahertz, okay? So we don't have a processor like that. People attempted, but designs didn't hold. It was too much heat, too much cooling is required. So, I mean, this thing doesn't work physically. So what they did, and what we have now, multi-core processors, and which means that you need parallelism in a single computer. You don't need to go for HPC clusters. Even on a single computer, you need to parallelize your codes. And this is the current paradigm for widely used libraries and codes also. Okay, and 1977, so von Neumann bottleneck. So this is John Bacchus. He received the Turing Award in 1977. And in his talk, he said that programming is basically planning and detailing the enormous traffic of words through the von Neumann bottleneck. And much of that traffic concerns not significant data itself, but where to find it. So this is the von Neumann design, right? So von Neumann architecture. And this is where you have the bottleneck. Because in the last 20, 30 years, processor technology, CPU technologies, they are evolving much faster than the memory one. So now, before maybe you need to put 1,000 data items, maybe 10,000, let's say 10,000 data items per second to feed, to utilize all the processing power. But now it is not 10,000, it is maybe 1 million, okay? So we have this, so you need to transfer the data that you have here to here very fast, okay? So, and this is the bottleneck you have. So it's a physical bottleneck, as just I described. It is also an intellectual bottleneck. So programmers at the time spent a lot of time thinking about code optimizations to stop lots of words being pushed back and forth, CPU and RAM. So the way you access the memory, in fact, has a huge impact on your performance. So I always say in my, I mean, everyone says it maybe, but so currently the cache in classical architectures, in multi-core computers, cache is your best friend, okay? They are there for a single purpose, to make the memory accesses much faster. And if you utilize them well, you can be 6-7 times faster easily. And if you don't accept this friendship, then you can be like 6 times slower easily, okay? So you need to understand the architecture a little bit, how the data is accessed, what happens when you access to a single memory location, which data is brought to the cache or brought to the core. So you need to understand these things if you want to do high performance computing. So we talked about that, and okay, this is processor, this is memory, and this is the physical von Neumann bottleneck, but there is also intellectual bottleneck. And there are and probably thousands of papers, research papers, scientific papers published in every year, trying to solve a problem due to von Neumann bottleneck. So this is the intellectual bottleneck part, in fact. So we spend time, researchers spend time, programmers spend time to optimize the data access here. Okay. So I told you that different applications utilize different aspects of parallelism, different aspects of components, in fact. So data-intensive applications utilize high aggregate throughput, server applications utilize high aggregate network bandwidth, and scientific applications typically utilize high processing and memory system performance. And this is the place where we use the HPC the most, in fact. Okay, there are some questions, and you can type your question into the Q&A section, and I will try to answer them in every 30 minutes or so. Okay, so microprocessor clock speeds have posted impressive gains over the past 2 decades, 2 to 3 orders of magnitude. We want to utilize them and have the highest performance that we can have. So current processors have multiple functional units and can execute multiple instructions in the same cycle. So even in a single core, in fact, you have parallelism. Maybe you are not aware of that, but you can have parallelism either by not doing anything or by using instructions, special instructions that are there to process multiple data items, maybe multiple integers at once, okay? Integer pairs at once, let's say. So the precise manner in which these instructions are selected and executed provides impressive diversity. Okay, so we have pipelining. I won't talk about that too much because this is GPU specific course, but what this CPU does is, so we have an instruction and we have stages on while processing these instructions, and each stage here utilizes a different, let's say, a different component on the CPU, okay, on the processor. So if we do this, get the instruction, perform multiple stages, get the other instruction, perform multiple stages. So this doesn't work because you use only one part of the CPU if you perform each instruction one after another. So we can have pipelining. So for instance, when we fetch an instruction, we are done. But when we are decoding that instruction, we can fetch another instruction, okay? So these stages are executed like that. So as you see, we have, in fact, some kind of parallelism here without doing anything because current CPUs work like that. Pipelining has several limitations. The speed up of a pipeline is limited by the slowest stage. So in modern processors, we have very deep pipelines, like 20 stages. So what is the bad thing about pipelining? Time to time, you don't know which instruction to fetch. before finding the result for the previous instruction. So you cannot know which path to go. Okay, so you know, if you know programming, I mean, you know programming since you are here. So there are if statements, conditional checks, right? And in typical program traces, every 5 or 6 instructions, we have a conditional check. So we need to check something, and based on the result, we will go either this way or this way. Okay, so and this is bad for pipelining, because in the pipelining, as you see, we are performing an instruction before executing this guy, before the end of the execution of this guy. So if this is a conditional branch, then maybe we need to get this one or this one. So how do we do it? Well, we predict. Okay, we predict the branch. We say that there are branch prediction algorithms. We say that, okay, so previous executions of this check resulted in this, these results. And based on that, I predict. So there is an algorithm that based on that, I predict this to follow this branch, and you follow that branch. So what happens if you are wrong? You need to do some rollback. Okay, so you need to go back. You need to alter the states back to the previous state, and after that, follow the next branch. So if you increase the number of stages, the penalty of misprediction also grows with the depth of the pipeline. Okay. So you can also have multiple two-way superscalar execution, maybe in this example, multi-way superscalar execution of the instruction. So you can have 2 components and you can do 2 things at once. And so these are, I mean, these are 3 different codes, 3 different instruction sets, not set, but the, 3 different programs, let's say, containing these instructions at each line to add 4 numbers. Okay, so this is really simple. So in this one, we bring the number from this address. The data is in the memory and put it to a register. So we bring the next one, and after that, put it to another register. Then we bring the next one and put it into the first register. We bring the next one, the last item, and put it to the second register. We add the register values, and after that, we store it somewhere. Okay, so in this one, we have a single register. So in terms of register usage, this is really good. We are utilizing only single register. We add the data on top of the value on the register every time, and we are done. And this one, in fact, this is really similar to this one. But let's see. So before we were using R1 and R2 consecutively. Now we are using R1, now R2, R2, and add R1, R2 and store the result back. Okay. So if you have a 2-way superscalar execution, for instance, well, you can run them in parallel, these 2 in parallel, but you cannot run these in parallel or run these in parallel. So you can still solve the issue. Why you can't use it? Because you cannot run these 2 things at once because they are writing on the same register. So this instruction depends on this one. You can solve the problem here by reordering the instructions. I will again briefly talk about that, but I will skip that. But this is already good for you. So you can do these 2, this one, and this one, okay? And this is the thing here, okay? So these 2 instructions, these 2 instructions, 3 and 4, and these, the 5th instruction and the 6th instruction. So the scheduling of instructions is determined by a number of factors. If you have superscalar execution, and your processor probably have it. True data dependency, result of one operation is an input to the next. Yes, this was one of the reasons. We also had resource dependency for this guy, right? Always R1 is used, the resource, you can consider that register as a resource. And there is branch dependency, we already talked about that. By the way, we have for loops, right? At every for loop iteration, you check some condition, in fact. So this statement here, every 5 or 6 iterations, you have a conditional jump, conditional check is really, really realistic. because in our codes, we have for loops, while loops, do whiles, etc., etc. And for each of them, you don't need to have if, right? So for each of these loops or loop kind codes, you need to have some condition check. Okay, so if you statically say that I want to run my instructions in the given order, this is in order issue, but based on the example, we can say that, based on the example here, we can say that, for instance, if you only allow in order issue, this thing is doomed. Okay, so you won't be able to run these two things, and one of your this part of your resource, CPU resource, it will be wasted. Okay. You can have out of order, so you can reorder the instructions. You can have a window and check, okay, what can I execute in the next 5 iterations? Okay, I'm getting this one, and then you can have a better performance. So if the second, so for instance, if the second instruction has data dependencies with the first, but third instruction does not, the first and third instructions can be co-scheduled. This describes the situation exactly here. You cannot execute 1 and 2, but you can execute 1 and 3. Okay. Okay. So we are doing these kind of things and to improve the performance and on a single processor. So I talked about wastes, resource wastes. I talked about predicting the branch, and so that is, I mean, that is just an example I use in my lectures. So suppose that this sort part is not here, okay? So you don't have it. And you have an array of random values, and you have a for loop over this array, and for every element you check, if your element is larger than 128, okay? If it is the case, you add it, okay? So you sum the elements in your array. If you sum the elements larger than 128 in your array, okay? So that's what you want to do. And you for some reason, you are doing it 100,000 times. So this is a dummy code, so it's not a real life code. In real life, you just multiply this number by 100,000, but I have this loop here to see the impact, okay? And if you don't have it, so this condition here will be either 0 or 1, and since this is modulo 256, there is 1/2 probability that this check will be evaluated to true, and 1/2 probability for false, okay? Yeah, and the branch prediction algorithm probably will not be good here, and this code takes like 20 seconds. But if you have that, if you sort the items for the first half of the loop, you will have, not the exact for the first half, but the expected thing is there. For the first half, expectedly, the values, the evaluation will be 0. Because the elements will be smaller, and the second part of, or the second half, or the second part of the array, it will be always 1. And the branch prediction will work really well here. So instead of 20 seconds, you will have maybe 2 seconds. So you will be 10 times faster. So just know your architecture, and it will pay off definitely. This is the memory wall that I've talked, the processor memory performance gap. It grows 50% year. So this is how the processor technologies in terms of performance goes, and this is how the memory technologies goes in terms of performance. So you need to talk about, you need to think about, you need to spend time about how you access memory more and more, in fact. And to solve this problem, as a remedy, we have multi-level cache hierarchies in our computer. So you see the words like L1, L2, L3. And this is, I mean, as I told you, this is your best friend when you do computation. So this is what processors work on. This is the closest place after register. So this is the closest place after L1. And we can have L2, for instance, caches in some processors. For instance, L1 and L2 per core and L3 per socket. Okay, this is a common thing that you can see on CPUs. And the size increases when you go down, but the latency also increases. The time that you spend per access, okay, so per one item, okay, the time that you spend per one item increases also if you go down in this hierarchy. So we have latency and bandwidth to when we talk about the performance of the memory system. And usually memory system and not the processor speed is the bottleneck, okay, for many applications. And this is why it happens, in fact, okay, the memory wall. So memory system performance is largely captured by latency and bandwidth. Latency is the time from the issue of a memory request. So you want to get some data, you issue a memory request, and you find the data, and some time passes, and you find the data available in the processor. So that time is the latency. But bandwidth is the rate at which data can be pumped to the memory, to the processor by the memory system. So one question is why they are not related. So if you increase the latency, then you reduce the bandwidth, right? But this doesn't happen because of the cache hierarchy there, and because of how memory system works. So when you go, in fact, you don't go and get, when you go to the memory, you don't go and get one item. You get multiple items. And the data can be fed, in fact, in a much larger pace. You go and bring multiple items, put it to the cache, and after all the memory requests, go and get the elements from the cache. So bandwidth is important, in fact. So it's very important to understand the difference between latency and bandwidth. So consider the example of a fire hose. If the water comes out of the hose 2 seconds after the hydrant is turned on, the latency of the system is 2 seconds, okay? So you turn on the hydrant, you wait for 2 seconds, and you have the first piece of water, okay? First water flow. Once the water starts flowing, if the hydrant delivers water at the rate of 5 gallons per second, the bandwidth is 5 gallons per second. So if you want immediate response from the hydrant, it is important to reduce the latency. If you want to fight big fires, you want high bandwidth, okay? So this is some analogy between latency and bandwidth and fires and hydrants. So we can reduce the latency using caches. So they are small and fast memory elements between the processor and DRAM. So this memory acts as a low latency, high bandwidth storage. If a piece of data is repeatedly used, that is important. We will talk about that. We will give this a name. The effective latency of this memory system can be reduced by the cache. So the question, there is a question here, can we improve a dot product computation with a cache? So if you go and bring only one item per memory access, the dot product computation, by the way, dot product, you all know dot product computation, right? So you have a vector, and you multiply each of these element pairs, corresponding pairs, and add them, right? But you use each element once. So if you go and bring one element per memory access, the cache will not work because there is no data that is repeatedly used. But if you go and bring multiple items at once and put it to the cache, and the next accesses will be coming from the cache, yes, I mean, you can improve that dot product still by using cache. So the fraction of data references satisfied by the cache is called the cache hit ratio of the computation on the system. And again, as I told you, this is one of the most important things that you need to consider if you are trying to improve the performance. So repeated references to the same data item is related to the temporal locality. So suppose that you access an item, and maybe you will access it 10 more times. So you can reorganize. I mean, there are algorithms in algorithm books. There are memory, there are time complexities, big O notation, master theorem. Yeah, they work, by the way. And they are really useful, especially if you are working with large data. And if you have n cube and square, for instance, computation, okay? But if you have like n log n, if you have n log square, and maybe even n square a little bit for small n, knowing the architecture is more important than knowing masters to or knowing big O notation, okay? Because caches will make you 6-7 times faster, maybe more, maybe less. So that depends on the application. But 5-6 is not a magical. I mean, it is a realistic number. It's not an unrealistic number. So suppose that you have a data item and you know that you will access it 10 more times. So you can reorganize things. You can reorganize your statements. Maybe you are increasing your time complexity. Maybe you are doing some redundant computations. But if you can make these 10 next accesses close to each other in timeline, okay, close to each other in timeline, then what you will have is what you will improve is temporal locality of that item, because you are accessing it, you are bringing it to the cache. So caches are small, and probably you will do more memory accesses, and there is a huge possibility that that item will be evicted from the cache because it will be overwritten by the next accesses if you do not access it in a close time. But if you make the accesses closer, then when you access next time, you will find it in the cache. If you don't make the accesses closer to each other, probably that item will be evicted and you need to go to the memory again, okay? So data reuse, again, as I told before, is critical for cache performance, and temporal locality is one important thing, okay? One of the two important things in terms of locality for caches. So don't hesitate, just try, okay? If you are coding something and if you say that, okay, there is 10 lines of code here and it takes like 50% of my execution time, which is again a realistic case for many computations. For HPMV, for instance, sparse matrix vector multiplication, well, you can write it in 3 lines, okay? So for loop, but probably you are using it like 100,000s of times, millions of times, maybe in a single execution, and it will take more than maybe 70% of your solver time, okay? If you are doing scientific computing. So you can reorganize it, you can play with it, you can say that, okay, this is the sparsity pattern I have, so I want to do these rows first, these columns, I want to divide the computation into 2, perform one strategy here, another strategy here. These are all papers, scientific papers, by the way. But then you will be faster because you are improving temporal locality. So for matrix multiplication, we have n square data accesses and n cube computation. So if you are multiplying 2 dense matrices, so we have n square elements here, n square elements here, n square elements in the result. So yeah, O n square data access. But we need to perform O n cube computation because we need to multiply this element with this one, right? No, this one. So you need to multiply one element with n elements. Okay, you have n square elements, so n cube computation there immediately. And you have also additions, okay. But we have the big O notation here. So there is something to improve here because each element is used n times. So if you apply something called tiling, we will see an example today for GPUs, you will improve the runtime significantly, and we will see the performance drastically improve without doing anything else. Okay. So impact of memory bandwidth. Increasing memory bandwidth results in higher peak computation rates. The data layouts were assumed to be such that consecutive data words in memory were used by successive instructions. Okay, so now before we were accessing one element multiple times. Now we are accessing different elements, but we are organizing the memory. We are not reorganizing the computation, the algorithm now. I am telling you that if you reorganize your data layout, if you reorder your data in the memory, because memory is one dimensional. So you will have also, you can have significant amount of performance boost due to spatial locality of reference. What do I mean? You access this guy in the memory, and then, as I told you before, you don't go and get only this item, put it to the cache. You don't do it only for this item. You do it for multiple items, okay? So we call it as a cache line. So this item may be in this cache line and you put it to the cache, right? So if you organize your memory layout such that the close items, items close to each other in the memory are accessed by consecutive instructions, then you improve your spatial locality of reference and you will have again 5-6 times more performance. Okay. So memory system is important. By the way, all I am saying here, they will appear in a different way on GPUs. For GPUs, we are always talking about CPUs here, but for GPUs, we have their counterparts. So exploit spatial and temporal locality, use your caches better. Try to understand if your application is memory bound or compute bound, and aware of that memory layouts and organizing computation can make a significant impact on the spatial and temporal locality. So hiding memory latency. This will be important for GPUs because in short, this is what GPUs will do. So as I told you, latency is important. CPUs brought this multi-level memory hierarchy. GPUs will do something else, okay? But that's the same problem. So in CPUs, we also have prefetching and multi-threading, but you can apply also prefetching on GPUs, especially in between host and GPU memory. GPUs have their own memory, physical memory. Your computer has its own physical memory. All I said before, the von Neumann bottleneck, you can observe it, in fact, in the PCI Express card, okay? Okay, that we still need to bring it to the GPU memory, then to the core. So we have another level of bottleneck here, but I mean, you can apply techniques like prefetching to put the data before it's needed here. Then at least you will get rid of this performance bottleneck. And the second is multi-threading. So let's talk about multi-threading and GPUs. Well, they have many 10,000s of cores compared to 200 cores, maybe 100 and something cores on a single CPU. So a thread is a single stream of control in the flow of a program. Yeah, we illustrate threads with a simple example. So here, we are trying to compute A times B. A is a matrix, B is a vector. And so that the output will be the C vector, right? And for each row of A, you need to perform a dot product of that row with P, B. And in a sequential execution, you can do it like this. In a parallel execution, you can create a thread which performs one dot product, and at the end you will have your result, okay? Since each dot product is independent of the other, these things can be executed safely without any communication, any extra overhead. But what you do is, let me see, yeah, okay. So the first instance of this function accesses a pair of vector elements and waits for them. In the meantime, the second instance of this function can access 2 other vector elements in the next cycle, and so on, right? After L units of time, where L is the latency of the memory system, the first function instance gets the requested data from memory and can perform the required computation. In the next cycle, the data items for the next function instance arrive, and so on. In this way, in every clock cycle, we can perform a computation. So what do we do here? So before, let me tell you that you don't need to have, you don't need to think that you have multiple cores. Suppose that you have a single core. That core will execute these threads, all of them, and there will be some context switching, and we assume that the context switch is fast. So there is not much overhead here. And for the first thread, there will be a memory access, and we will pay the latency, right? We definitely need to pay the latency for that one. For the, and when that thread is waiting for its data, another thread can come and say that, okay, I also need data, and I am going to the memory subsystem. Then it starts to wait, and you can go to the next thread and get, again, perform your request, memory request. Go to the next one, perform your request. But after some amount of time, the latency, the data pair that you need for the first guy will be there. So you are overlapping the latencies, and you can perform the computation at that time while other threads are waiting for their items, right? So you are hiding the latencies. So the latency is still there, but you are assuming that the memory system is powerful enough to feed all these data, assuming that this approach doesn't reduce your cache utilization, assuming that context switch doesn't have too much overhead. This approach is really good. And this is what GPUs does, okay? In a slightly different way, we will have also other techniques to improve the performance, but this is how you hide the latency. You have many things going on on the device, on your CPU, processor, GPU, processing unit. And whenever a data access is done, okay, do it. I don't care. Because I am going to the next one. I will not wait for you, for your data. I will still work. I will perform other data requests, maybe some meaningful computations, but I'm hiding the latency here. The latency is still there though, okay? Okay, so this is how GPUs will survive without these caches, in fact, because GPUs will do it with 10,000 cores. And we were talking here a single core, okay? Okay. So prefetching, well, this problem is the same. You miss on data loads and you wait, right? And multi-threading was hiding the latency. So here there's a different solution. If you know that you will miss on the data load, on the next data load, you can make it early. Okay, you can bring it to an early place in the timeline and say that, okay, I'm performing it here. And after that, whenever you need it, probably you will wait less. Okay, maybe you won't even wait. Okay. So the only drawback is that you might need more space to store advanced loads. So cache, okay, you are bringing the data to the cache, in fact. So cache is limited. So if you do the memory request too early, then probably that item will go and will come to the cache. And maybe another data access will evict it from the cache. So that will be the problem. If you do it too late, then you will wait, okay? So there is also an optimal time for the prefetching. Okay, so one example is, so without prefetching, you do something, you load data A, you wait for that A, and this is the latency. You do something with A, you load B, then you wait for B, and you do something again, okay? So you can prefetch A and B here, and they are brought to the memory while you are doing something. And then you load A, it will be immediately there, and you load B, it will be immediately there, and then you don't need to wait for these guys. So instead of this much time, you will have this much time, this much execution time, in fact. Okay, so as I told you, bandwidth requirements of a multi-threaded system may increase very significantly because of smaller cache residency of each thread. So instead of the whole cache reserved for a single thread, now you have the whole cache. Maybe you have 10 threads, so 10%, you can assume that 10%, it doesn't work like that, but 10% of the cache is reserved for a single thread, okay? So multi-threaded systems become bandwidth bound instead of latency bound because you hide the latency. So you can increase the number of threads. So the reasonable question is, let's make the number of threads 1 million, 2 million in a CPU, okay, not GPU. It won't work because maybe you are limited by the operating system, by the way, so there is that limit. But if you are not limited, I mean, your memory subsystem will not be able to feed all these threads, okay, at once. So multi-threading and prefetching only address the latency problem and may often exacerbate the bandwidth problem, yes. Multi-threading and prefetching also require significantly more hardware resources in the form of storage. Okay, we talked about that. So the control structure, as I told you, this is important, and this is one of the things GPUs get rid of, let's say, okay? So control unit is good because it operates, it operates the processor. It says that, okay, do this, and then do that, and then do this, etc., etc. but it also brings some complexity to the system, okay? So in a machine cycle, the instruction is fed. By the way, the programs are also loaded in memory, right? So you need to bring the instructions first to the control unit and check, okay, what we need to do for this instruction. So I need to say something to the ALU. I need to say something to the data pad, and they need to do something for this instruction. And the control unit handles that. He codes, handles everything, and after that, he controls the ALU, the arithmetic logic unit, so the thing that actually performs the operations. And then the command is executed, so the result is written back to the memory, and it's a cycle. So right, this is a machine cycle. Okay. So processing units in parallel computers either operate under the centralized control of a single control unit or work independently. Okay, so both of these, so either operate under the centralized control unit of a single centralized control of a single control unit or work independently. These both exist on a GPU, okay? And we will see how. If there is a single control unit that dispatches the same instruction to various processors that work on different data, the model is referred to as single instruction stream, multiple data. We have a single instruction, but that instruction will be executed by multiple data. Consider vector addition. We will again see an example today. What you do is the same. Vector addition. So two vectors, you want to add them, you have another vector, but for these pairs, you are doing the same operation, right? So you can in fact represent that with a single instruction, the addition, okay? The memory addresses will change though. So the data will change. So single instruction stream, multiple data stream. Not all the computations are suitable for this pattern, but GPU vector addition, it is suitable. Matrix addition, it is suitable, okay? Whatever addition in multidimensional data, because these are pairwise additions, right? They are suitable. So if each processor has its own control unit, each processor can execute different instructions on different data items. This model is called multiple instruction stream, multiple data stream. So they are independent from each other, okay? So these things can, each processor are doing different things at different times with maybe different data, maybe with the same data, but they are doing different things, okay? So that's the important thing in MIMD. We can skip that. So SIMD processors. So we are going to GPUs, in fact, step by step. So we are still talking about CPUs though. So some of the earliest parallel computers belong to this class of machines, SIMD processors. So variants of this concept have found use in co-processing units such as MMX, SSE, AVX, AVX 512 units in current processors, in fact, and not on Intel processors, not on only Intel processors, also other processors have their vectorized, this is how we call them, vectorized instructions, okay, or vector instructions. So SIMD relies on the regular structure of computations, such as those in image processing, and GPUs apply this paradigm within a single warp. Let me see, yeah, okay, so that's one example. Maybe not a good example. So let me talk about a good vector addition example again. So how you perform it in a usual instruction, usual instructions, traditional, not the usual instructions, let's say, non-vector instructions. You go and get this guy, you go and get this guy, put them to registers, add them, store the results back, right? So in vector instructions, you have registers which are really wide on CPUs, okay? So 512 bits, maybe. So considering that, maybe you have 32-bit values, floating points, single precision floating point numbers. So 512 divided by 32, 16, right? So you can put 16 floating point values onto a single AVX 512 register. You go and get from the memory 16 values, put it to the register. You go and get 16 other values from the other vector, put it to another register. Now you have two registers, which are 512 bits. When you want to add them pairwise, there is an instruction designed for that. So you say, okay, add these values inside pairwise, in a pairwise manner. You store the result, maybe on another register, maybe on one of these registers. but at the end you will have a 512-bit registers, 512-bit register, which contains 16 results. And you write this to the memory. So you do 16 operations at once. You are not 16 times faster, okay? Because this interaction is more complex, so you need to perform more cycles. But still, I mean, you will be like maybe 7 times, maybe 8 times, maybe 6 times faster easily. Okay. So there is one problem, the conditional execution. So how do we solve that? So let's consider that we have this processor 0, processor 1, processor 2, processor 3 controlled by the same controller. Okay. So they need to do the same operation every time, but there is an if statement here. So the question is, you need to first decide which processes will work. Okay. So suppose that these are the initial values of A and B and C. SIMD, they will work with their data, multiple data, but they need to do the same operations. Okay. So if B is equal to 0, B is equal to 0, yes. B is equal to 0, yes. So these processor 0 and processor 3, they will work. The others will wait, but they will work at the same time. Okay. But the other processors will wait. So this is how you solve this thing, the conditions in SIMD processors. In the else part, processor 0 and processor 3 will wait. So processor 1 and processor 2 will work, and they will add their result. Well, they will not add, they will divide A to B, sorry. So C will be 2 here, 1 here. And after that, you are done. So now you can, I think, guess that if you have SIMD architecture, you don't want conditionals. You don't want branches in the program execution, right? Conditionals, maybe if every thread saying that, okay, I will, every core, every processor says that I will work, conditions will not hurt, but if it branches too much, then you will have a problem in terms of performance, because at this time, we waste the processing power of these two, they became idle. At this time, at the second step, the processing power of processor 0 and processor 3 will be wasted, okay? And this is one of the important things that you need to consider when you do CUDA, when you do GPU programming, because we will see that some number of cores are controlled by a single controller. So you need to be careful about the branching inside the code pieces executed by that part, okay? We will call that a warp, and we will see that in more detail later. So there are 2 primary forms of data exchange between parallel tasks, accessing a shared data space and exchanging messages. Platforms that provide a shared data space are called shared address space machines or multiprocessors. Platforms that support messaging are also called message passing platforms, which we will not cover today. We will not touch in any way. But the message passing platforms, that model is suitable for HPC cluster supercomputers that are that contain multiple nodes. Okay, so there is an interconnection network in between, and you can pass messages from one node to another by using libraries like MPI or standards like MPI. And advanced interconnection network, there are other problems here, but they are all based on the similar problems that we are talking here. There is some memory, which you can consider as remote memory, and you are trying to get data from that remote memory in a fast way and put it to your local fast memory. On a single node, registers are your close memory, maybe L1 cache, you can consider it as your close memory, and the actual memory is your remote far memory. On a multi-node computing environment, the network will be the maximum latency, because within a node you won't see these times, these message preparation, message sending, routing, muting, etc. So these things will not work there, will not be there. So your memory will be your fast memory. The memory of another node will be your remote memory. Okay. So we are all based on the same problem, in fact. if either when you do message passing or when you work on shared address space machines. So in shared address space platforms, part or all of the memory is accessible to all processors. You can have multiple cores, right, in a single node, and you have a single memory. So all the memory is accessible to all cores. In fact, processors can interact by modifying data objects stored in the shared address space. So one can write, the other can read. So that's the communication medium, in fact. If the time taken by a processor to access any memory word in the system, global or local, is identical, the platform is classified as uniform memory access, else a non-uniform memory access, NUMA machine. If you have multiple sockets, for instance, in your machines, 4 sockets, each containing 8 cores, each socket has its own memory unit, okay? And let me see if I have a slide for that. Yeah, okay. So, I mean, this says interconnection network, but, well, you can consider this also the memory bus, I mean, memory subsystem, okay? So here, for instance, you have a processor, you have a cache, right? And even if you have a single memory here, single memory unit here, let's assume that you have single memory unit, that cache access will be faster for this processor compared to this guy. I mean, this guy will not be able to access your cache directly, but you can consider that there is a memory location. Okay, it's a cache, not actual global memory, but that guy can, I mean, the access to this guy is slow because that thing first needs to be written here, and after that it must be read here. So that is non-uniform. But it says uniform memory access, shared address space, blah, blah. But if you consider cache also memory locations, then you have NUMA. This is actually what NUMA is. So, and traditionally, what people call NUMA. As I told you, if you have multiple sockets, so consider this processor here as a socket containing multiple cores. There will be a memory unit connected to this guy. There will be another memory unit connected to another socket and another socket. So you can have 4 socket, 8 socket machines nowadays. And that thing now is accessible by this guy directly, but the access time to this guy will be slower compared to the access time of this guy to this guy, okay? So this is what people call as NUMA. So it is 11:30. Okay, so it's important to note the difference between the terms shared address space and shared memory. We refer the former as a programming abstraction. Okay, so the shared address space is a programming abstraction, and the latter is a physical machine attribute. So shared memory machine is a physical machine attribute, but even if you have multiple nodes which do not share memory, so there are different memories, okay, physical memories, but you can have libraries on top of this system which make these memories in a unified, which unifies these physical memory locations, and you can program it like a shared address space machine. So you can say that, okay, I want to access that address, but that address can be on another machine, but you don't know it, so it's abstracted, okay? So you don't see it, but there are libraries that does it for you, so you can write a program, and whenever you request some data from some memory, it can either come from your local memory or a remote memory. So this is the shared address space. When we say shared address space, this is what happens. So this is a programming abstraction. Okay. So let's stop here for a, let me see, yeah, for 10 minutes. And in the meantime, you can put your questions here. So it's 11:34 now. So let's be here at 11:45. Okay, 11:35 now. 11:45, so 10-minute break. And in the meantime, you can put your questions to the Q&A session and I can answer them. Okay, so it is 11:45. Let's go over the questions. So can you use slipstreaming in this case? So the pipeline case to determine which instruction to pick next. Well, there are processors who are doing that. Probably yes, so the answer is yes. And there are also some solutions recently. So by performing some redundant operations, a similar technique, I know some research papers, but I need to find them. I read them recently. So yeah, the answer is yes. Can the bandwidth alter during a process, during a total process? The bandwidth, the maximum bandwidth, it doesn't change. It is in fact theoretical. But if you are asking if you can write the same code, same process, if you can do the same thing in different ways and the bandwidth changes, yes. Because the memory bandwidth that you reach, your bandwidth utilization depends on how you access the memory. So that changes. Okay, so that question, are you going to share the slides or lecture videos? Yes. I will put the slides and I will also, we will also share the lecture videos. So there is another question. What is the most state-of-the-art solution for the von Neumann bottleneck? As you told, there are always some suggestions for the solution of the von Neumann bottleneck. So there are physical and intellectual von Neumann bottlenecks, and I was talking about the intellectual ones. The solution depends on the problem, how your data is there, how your data is organized, how your computations are reorganized. So you can always, not always, but almost always do something by using techniques from the literature for your problem. Physically, there's an architectural question, and people are trying to bring the memory closer to the processor, the CPU guys and the GPU guys every time. So they are adding more cache, more shared memory, and other architectural tricks that I do not, maybe I am not even aware of. So the intellectual part, yeah, almost always some suggestions are there. Physically, I mean, it depends on the processor that you have. There is another question. Thanks for this precious lecture. Okay, where can we get the recording? It will be on the same web page, the Indico web page that you use for registration. So there will all the sessions will have their own videos, and the slide sets will also be reachable from there. Another question. Does the cache of the modern processors or GPUs be used for read-ahead purpose only to increase hit rates, or do they serve also as write-back cache, having some kind of link to the memory subsystem? They are being used for both, as if I'm not mistaken. So read-ahead purpose, well, prefetching already does that, and we put it to the cache. So, and the write-back cache also is something that you see in modern CPU designs. So my answer is yes for these two. Okay. So if there are no more questions, let's go back to the slides. Now, after seeing all these things about computing, performance, let's talk about briefly on GPUs. Okay. So CPU, you can consider it as a fast sports car or a motorcycle here. You can carry less people, maybe one, maybe two, maybe three. but it is fast, okay? So we are talking about in terms of latency here, by the way. So we have our cache here to reduce the latency significantly. Again, many optimizations are possible, and they are specific to problem, specific to computation that you have. This is why we have many papers in the literature and not only one or two. For instance, I am interested in sparse data, graph operations, sparse matrices, tensors. So I am aware of the techniques that people use on these things. For dense data, you can also apply things like tiling. We will see one example of that today. So there is cache and there are optimizations. You reduce the latency, but you have only a number of cores, okay, here. A number of processing units, not a number of cores, sorry. A number of processing units, a few number. But with GPUs, you have your memory. Nowadays, GPUs can have like 80 gigabytes of memory. Before we were calling them as memory restricted devices. Nowadays, it is unfair, especially if you have money. When you don't have money, you are still memory restricted. But you have thousands of cores, thousands of processing units, but you don't have that complex cache hierarchy here. So your latency will be high, but remember the technique that we used, the multi-threading. We were doing context switching and perform the memory requests, and while waiting for them, we were doing either another memory request or meaningful computation. So we were hiding the latency. And this is what GPUs do, okay? You transport many people on a much slower device, vehicle, like a bus. And also the frequencies of CPU cores and their complexity, much, but much lower than, let's say, compared to the CPU cores. So you can have 2.73 something here, maybe 1 gigahertz here or 3 gigahertz here. And you do other techniques like pipelining, multiple units like this one, and you don't have this here for a single core. So we have complicated, sophisticated cores that can do a few operations, but really fast. We have many cores, thousands of cores. They are simpler, but they perform. When you combine their power, they can be much faster than a CPU, especially your application is suitable for it, okay? So these are the main differences between the CPU and the GPU. So GPU performance is pulling away from traditional processors. This is NVIDIA single precision performance, NVIDIA double precision performance. These two also differ, and we will talk about why briefly. And we have CPU performances here again, single precision and double precision. So this is not 2020, but close, I think 2016, and we can have, in fact, made much more than that now. We will see some numbers. But like 7-8 times theoretical, that is important, theoretical gigaflop, the billion floating point operations gigaflop per second, and the value is much higher for the GPUs compared to CPUs. Does it mean that the CPUs will fade away? No. I'm emphasizing that this is theoretical. I am emphasizing that the performance difference is coming from the suitability of the application, and we have operating systems. So operating systems are not that suitable for these kind of things, for GPU kind of things. NVIDIA is producing now its own CPU, even. I mean, so they're also on that domain now. Okay. And this theoretical peak gigabyte per second. So this is the memory system performance again. And as you see, for CPU, the value is lower. And for this guy, for GPUs, it is much, 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 much higher. Why? Again, remember the example that we used, multi-threading, so context switching and latency hiding. I told you that the memory system must be powerful. It must feed all these threads working on the CPU and each of them are doing dot product, right? For GPUs, it is worse. For GPUs, you have 10,000 cores probably simultaneously being executed, maybe 100,000 threads, okay? There is a limitation depending on the GPU technology that you use. But I mean, hundreds of thousands of threads simultaneously. So you need to feed them and you need to have a much higher memory system feeding performance, okay? So this means that you can push 700 gigabytes per second from the DRAM that you have on the GPU to the GPU cores, okay? So what this gives you is energy efficiency. So this is the computational efficiency chart, and these are GPUs, and this is gigaflop per watt, okay? So if you are here, let me see, and this is gigaflop per area. So if you are here, that's good, okay? And GPUs are there. GPUs are usually more energy efficient than CPUs. But again, since this gigaflop per second, there is a theoretical value and there is a practical value. This is again for some applications, not for all applications. So these are recent ones. Let's talk about the real today's numbers. FP32 performance is for A100, by the way. You can have either the 40 gigabyte version, 80 gigabyte version. And the FP32 performance of this guy is 19.5 teraflops, which means that you can perform 19.5 tera operations, okay? 10 to the 12, okay, 19.5 times 10 to the 12 floating point operations per second, which is amazing, which is an amazing number. FP64 performance is half of that, okay? So if you do double precision, if you want your accuracy to be higher, like we usually want to have in scientific computing, in solver business, then you have around 10 teraflops. And recently we have other things, other types of cores, specially designed for performing multiple operations, again, at once, tensor cores or AI cores. In fact, there are also these things. So you can, if you utilize them, you can have more performance. So there are these kind of GPUs. They are good for scientific computing. Their double precision performance is really nice. And there are these type of GPUs. This is GeForce RTX 3090, like 24 gigabytes of memory. But this is not the thing that I want to show here. Where is it? Okay. So FP32 performance is 40 teraflops, faster than them, faster than this one. And this card is, I think this is more expensive. A100 is more expensive. But FP64 double precision performance is only half, maybe half teraflop. Yeah, 625 gigaflop. Compared to this one, it is much less. So this card is very good on 32-bit single precision operations. And as you see, the cache sizes are not very large compared to the CPU cache. So this is like AI. This is an AI card, and this is a generic data center card. Okay. So what GPU wants to do, don't forget, we want to hide the latency. And this is how we improve the performance. SIMT, now you know it, single instruction, multiple threads. They are working in an asynchronous manner. And the memory must be really powerful to feed all these threads, okay? So this is also important. Okay, so CPU minimize latency within each thread. That is what we want to, what we have in fact, okay, with this advanced memory hierarchy. So this is, for instance, let's see, this is the context switching, this guy. So its overhead is not that much compared to task sizes. This is waiting, okay? So this part is waiting. You are waiting for your data. And this is actual processing, okay? And this is the ready part. And yeah, I mean, you don't have it on here. So for instance, you perform a memory request for T1, thread 1, and you do some computation. You perform a memory request, you perform some computation, and you do some context switching, you do something for T2, memory request, computation, memory request, computation, and et cetera, et cetera. In GPU, we have warps. And as you see, the waiting time is significantly more compared to the CPU waiting times. So latency is higher, okay? And time also, the warps are scheduled. So we will talk about that in detail in a very efficient manner with zero overhead, we say. And then you perform some processing. So you wait a lot, you wait even when you are ready a little bit, but these are overlapped, okay? So once you are doing some computation, so after this, by the way, let's see, after this point, you see all we hear is green. So we have a green part after this point, after this line. So we do not lose processing power, in fact. At some point, the warp is working, okay? At some point, at least one warp is working on the device, on the processing unit that does something with the warp, okay? That runs a warp, let's say. So we don't lose anything. But the latencies are, although the latencies are higher, they are hidden, okay? So this is why GPUs can be faster, theoretically, compared to the CPUs. We already talked about that. CPU, single instruction, multiple data, simultaneous multi-threading, single core can perform multi-threading. That is, you don't need multiple cores to do multi-threading. In fact, you don't need multi-cores for multi-threading. Let's say it like this. GPU, single instruction, multiple threads. A CPU core, we call it as a streaming multiprocessor. Okay, so this SM. The working unit is a set of threads, 32 threads. We call it as a warp, and these 32 threads are controlled by a single controller. So within a warp, you don't want branching, because we saw that for SIMD, if you have SIMD or SIMT, if you have multiple branching in your execution, your performance will be less because you will waste your, you will waste your processing power, okay? In our example, there were two cases. So if A is equal to 0, do this. A is not equal to 0, do this. Consider a conditional that have 10 cases. So you have 32 threads. They will be distributed into these 10 cases, sub-cases, right? And at each case, only 1 or 2 threads will be working probably, and the rest will be waiting. So we don't like branches for this reason. We have a single controller. We have a working unit called warp, which is being controlled by a single controller, and they are doing the same instruction always. If they are not doing the instruction, the same instruction with another thread, they wait. Okay, so memory, GPU memory is not the CPU memory. You have a different memory here. So 40 GB, 80 GB, 24 GB, we saw examples. And this is the host memory, but unfortunately your data is here. Initially, your data is in the host memory, not on the GPU memory. So you need to bring that data first to the GPU, okay? And this is another bottleneck here because the PCI Express communication ports that we use is not that fast. So consider the 7, let me see. Yeah, this is the interconnect. Okay, here, there was a number here. 700 gigabytes speed, okay, 700 gigabyte per second speed from here to here, from this DRAM to cores, but like 30 gigabyte per second speed from here to here. So that's your bottleneck now, because you need to bring that data, something here to these green parts. These are the processing units. So first you need to bring it from here to here with 30 gigabytes per second. And you need to bring it from then here to here with 700 gigabytes per second. So it doesn't hurt. This doesn't hurt compared to this one. So I told you that GPU memory is no CPU memory. They are separate physically, but there is unified virtual addressing. So you can use the same type of pointers. And you can say, okay, I am getting the address of that memory location. So this is still an address. I mean, it's unified virtual addressing. So memory transfers need special consideration. You need to do them as little as possible because that's your bottleneck. Okay. So formerly, what we do was for each, and it is, I mean, in the earlier versions of CUDA, what we do was we have the data here. We say that GPU computation has 3 stages. You first bring the data from host to device, do the computation there, and get the output from device and copy it to the host. So host to device transfer, computation on the GPU, device to host transfer. Before we were doing it like that. But nowadays, you can have a memory, a data, okay, so let's say a data stored in the memory, and you can say that your CPU cores, okay, modify it, or GPU cores access it, modify it, okay? So this is handling behind the scenes automatically. We will see again one example, but doing things manually give you the chance to optimize them further. So I still perform the first thing because this is how I learned GPU programming. If the data is not that huge, okay? If the data fits to the GPU, I do it automatically. So I do it manually, sorry. But let's, even the data, when the data doesn't fit to the GPU, if you reorder your computations to make the same data sets accessed in a close time interval. Now, again, we are talking about spatial locality, temporal locality kind of things, right? And you can consider that part is your cache, as your cache, and that part as your memory now. Because you bring something here, this access is faster, this access is slower. It is the exact same thing when you access from here to here. This is faster, this is slower, right? So you can consider this as your cache, a little bit large, very large cache, maybe not as fast as your actual cache, but this is the remote memory for the GPU. This is the closed memory for the GPU. And if you use the same analogy, you can use the existing techniques from the literature easily. Partition the data, divide the data into small sets in a nice way, such that the computations happening are accessing the same data sets always. And whenever you are done with it, you can get it back. So there are partitioners in the literature just for that purpose. So we also have unified memory now. This is what I've told. And we have different technologies to connect GPUs to the hosts. So instead of PCI Express, you can use NVLink. Well, at that slide time, it is 80 gigabyte per second transfer time. So maybe it's different now a little bit, I don't know. Okay, so CPU versus GPU, let's summarize. CPU, they are optimized for low latency. There is a large main memory, fast clock rate, large cache, branch prediction, and powerful ALU. Relatively low memory bandwidth. Cache misses are very costly. You want to reduce them as much as possible, believe me. And low performance per watt. GPUs, if you have a single task, they are not good for you. If you have multiple tasks, multiple things, millions of things to be computed, millions of operations, let's say, they can be good for you. So they are optimized for high throughput, high bandwidth main memory, because you need to feed these cores as much as possible. They are latency tolerant because latency is hidden. There are more compute resources, high performance per watt, but they have limited memory capacity. And nowadays, 80 gigabytes is good, but for real life scientific applications, you will need much more. So that you can still say that they have limited memory capacity, low per thread performance, and they are extension cards. So you need to connect them to the host through a channel, which will be your bottleneck probably. Okay. So let's go back to the questions. Are there differences between 32 warps and 64 warps? I mean, other than the scientific precision in outputs, as you taught for sure. So there is no 62 or 64 or 32 warps. A warp currently, I mean, in current GPU designs, it may change later, has 32 threads, okay? If you have 32 warps, then you have 1024 threads. And if you have 64 warps, it is 2048 threads. But if you are asking the precision, 32-bit single precision or double precision, yes, I mean, for double precision, you are processing 2 times more data because you are using your more bits to store the values in a more accurate way. And especially if you have an AI-based card, which is optimized for 32-bit operations, and maybe some power of some 64-bit power is hidden, then you need to be careful. Yeah, there is a significant difference between 32-bit and 64-bit computation. Okay. Any questions? Okay. So let's start. Let me close this one. Oops. Let me open this one. Okay. Okay, so now we will talk about CUDA. So we will have an introduction to CUDA. C, it's a C, but I mean, it is the same with C++. Okay, so where CUDA C fits in the big picture? There are 3 ways to accelerate your application. You can use existing libraries, which I suggest frequently to my students, to the people that ask me to, okay, how can I use a GPU? I like programming GPUs. I like programming any device, in fact, having thousands, millions of cores. It is nice. It's a nice exercise. And this is how I earn my money. Okay. But if you are not used to that, if you don't know programming, there are libraries, in fact. If you don't know advanced programming, there are libraries which are exact for GPUs. when you use when you do machine learning, for instance, you don't need to use CUDA. When you use machine learning, you can either use maybe TensorFlow, Keras, I mean, maybe Keras behind TensorFlow, or TensorFlow behind Keras, or PyTorch, and the codes that they use behind the scenes, they are already exiled for GPUs. So you can, they submit the task to the GPU automatically, and this is, again, seamlessly happening. You don't know even what the impact. So this is easy to use, and you can have most performance because these things, these libraries are built by people who are experts on that, okay? There are compiler directives, easy to use, portable codes. So maybe the libraries is not that they are not answer for you, okay? So maybe there is no library to execute your custom code. So you need some parallelization, manual parallelization. And the first thing that you need to try is compiler directives if you don't know how to write device-specific code. We will see some examples. So with some compiler directions, okay, compiler, I am doing this computation, this is the input, this is the output, offload it to a device, offload it to the GPU that I have on my machine. Okay, so you can still say things like that. And the next thing is programming languages. This is the most performance, again, with this as the libraries guy. Library developers are having the most performance. You can also have the most performance, but for your computation, which is not supported by any libraries. And they are the most flexible ones because you can use your device in any way you want. You are programming it now, okay? So libraries, easy of use, drop in, and their quality is probably high, especially when they are developed by companies like Google, Facebook, Amazon. So, I mean, they have a significant software engineering process already, and they are high quality. Their APIs are there, documentations are probably really nice, well written, so you won't have a hard time to use them. And there are libraries also from NVIDIA, I forgot NVIDIA, like QDNN, TensorRT, QSolar, QSparse, QBLAS. So graph operations, MVGraph, for instance, Trust. We will see again one example for this, very, very brief example, QFFT. So we have, I mean, many libraries around. And for instance, the machine learning libraries that you use, they are using another library, another linear algebra library on the backend. Okay, so to do matrix operations on this machine learning processes, deep learning processes, and tensor operations also. So there is a library which is using another library, and you are using that library. In fact, there is a hierarchy even here, and it is seamless. You just need to install them correctly, and that's all. So Trust, for instance, you can say that I am creating a host vector. So that's a vector on the host on my server, okay? And I am initializing elements. And after that, I can resize it. I can print the contents, blah, blah, blah. And then I can initialize a device vector. This time there's a vector on the GPU. And I can create it from H very, very easily, seamlessly. So you don't say, transfer this memory address and the rest to the GPU and give me the pointer. So you are not interested in this kind of coding. And you can easily say D is equal to H and you are done. So you can change again, elements like that. You don't need to say, okay, there is this address on the GPU on the device. I want to change it. So you don't need to say things like that. You just need to say D0 is equal to 99, okay? So what you can do, for instance, with CUDA is create a variable called I or dummy, put 99 inside and say that, copy this, this content, this address here, which is 99, to this memory address. So you can do this as I described now, but Instead of that, you say by using a library D0, okay, it's 99, that's all. Anyhow, so these are possible. And you can do the additions like this. For instance, you have two host vectors. Let's see, three device vectors. So you can you say copy this vector here, host vector to the device vector 1. Copy host input host vector 2 to the device vector. And then there is this transform operation, which is a multi-purpose thing. So you just give the operation here, and it performs the operation pairwise for each element in the vectors. So input 1 begin, input 2 end, input 1 end, and input 2 begin. And that's the output place. You don't need to specify your input 2 end because you already know how many elements are there. So you don't need that. And the output is here, and perform this operation. Plus, so it's addition on this type of data, float, single precision, floating point number. So you can use these libraries like that and perform vector additions. On the contrary, that we will do it today with CUDA. Okay. Compiler directives, again, they are easy, portable acceleration, but performance of code can vary across compiler versions because compilers try to optimize the computation that you give. And they may not, they are really good, by the way. Compilers are like beasts. Okay, so the literature on the back end of the call for compiler technologies is huge. And they are really good optimizing codes. I mean, maybe better than you, okay? But for some of them, for some computations, especially if you are using a different device, I mean, you may do better a little bit. So because you are more flexible on programming that device. So this one, for instance, suppose that you have a loop like that, again, vector addition. Output vector I element I is equal to input vector element. Input 1 element I, input 2 element I, and you want to do this operation, right? So there is this pragma. We call them pragma, compiler pragmas. So this is pragma ACC. Okay, so that will handle it. Okay, parallel. Okay, perform a parallel operation, and there is a loop coming. And this is the data that I have, and this is the output data I have, and perform this operation on the GPU. So automatically, you don't do it manually. This thing is copied to the GPU. This thing is copied to the GPU. This operation, this loop is performed on the GPU, and the result is written back to output array on the host, okay? So that is done automatically without you even realizing. And you put this pragma here, compiler directive here. So programming languages like CUDA, you have the best control of parallelism. It is the most flexible one. You can try anything you want, but you need to write more code, definitely, okay? So you have CUDA-C, CUDA-C++, CUDA Fortran, PyCUDA. I mean, these are all possible. And MATLAB also use CUDA, can use CUDA behind the scenes, etc., etc. So we have many alternatives for GPU programming languages. And today we will talk about that. Okay, so the vector addition example. How do we do it? So that's the question now. And we will see some examples, some CUDA codes, sample CUDA codes to do. So we have two vectors. We want to add them, A and B. We have two vectors, A and B. We want to add them and have C. Okay, so this is the operation that we want to do. Okay. So this is still CPU code. You are familiar with the pointers probably. So this is an address in the memory. This is an address in the memory. This is an address in the memory. And this represents the first vector. This represents start of the first vector, start of the second vector, start of the output vector, and then the number of elements. Since all vectors are equal sized, we have one and here. And this is the code you write, okay? Okay, so there is a comment. Also, there is a new compiler, Intel DPC++, which support NVIDIA GPU. Yes. I didn't try it, by the way. I use CUDA and I am having fun with it. So, and you call that function. So that's what you do. So the memory allocations, input initialization, everything is done here, and you call that function and you are done. So here, by the way, with CUDA, you can still do your computation, some of your computation on the CPU. And whenever you think that that part is good for the GPU, okay, I am putting it to the data, I am performing the computation, I am getting the data back, the output back. So you can do heterogeneous computing. It's not like you are solely using GPU. You are using CPU and GPU at the same time. This is one of the beauties about it. So part one, we allocate device memory for A, B, C. We first need to allocate the places that we will put our data on the GPU. So we will say that, okay, give me that much memory, give me that much memory, give me that much memory. Then we'll transfer the host data to the GPU data, to the places that we just allocated. And then we will get the output back to the CPU, okay? So this is what we will do. And we need to free the device vectors that we have allocated here. So let's do it. So this is a good convention for host array. If you do heterogeneous programming, if with CUDA, for host arrays, you have H here. So this is host A, host B, host C. And this is the D device versions of them, DA, DB, and DC, okay? So let's do it. Let me see. Okay, so let's go over these. Let me see. Yeah, let's go over these first, and after that, I will go back to the slides explaining these functions again. So vector add function, I have the host vectors given to me. The size in terms of bytes for each vector is computed like that, n times size of float. So which will be 4 times n, because size of will return me 4. And I have the declarations of the pointers here, device pointers declarations here. Then I do this. Okay, so this is a little bit confusing at first, but it is not, believe me. I know how many bytes I need for each vector. So CUDA-malloc allow me to reserve some space on the GPU of that size. And the first location, the starting location of that region, memory region, is now stored after this function, is now stored in DA, okay, that pointer. And I do the same for B, I do the same for C, DA, DB, DC, okay? Then memory allocations are done. So at the beginning, I have that configuration. HA, HB, HC, they appear on the host memory. I don't have anything on the device memory. Once I have these red lines, these red statements, once I execute them, the DA, DB, DC are now reserved for me. Then I do the transfer. Okay, transfer is done. Basic transfer is done. CUDA memcopy. There are advanced versions of it, but this is the most widely used, let's say, especially if you're a beginner, you just transfer it with CUDA memcopy like that. This is similar to the memcopy in C. So you first need to have the destination address. Destination location for this transfer is DA. Source location, the data that you will copy. So this is destination source, right? In memcopy also is HA. So you want to transfer the data in that location in HA to DA. How many bytes do you want to transfer? This is size. One simple error everyone makes at the beginning is you give the number of elements here. No, it is the number of bytes you want to transfer. So this is type independent, in fact. So you give the number of bytes that you want to transfer, not the number of elements. And then we have the fourth parameter, which specifies the direction of the transfer. Why do I need the direction? I mean, I have already device pointer here, host pointer here. These things are unified, right? So they are coming from the same address space. So you need to say that still, okay, I have 2 pointers and I want to transfer this from host to device, okay? So CUDA mem copy host to device. And I do the same for B, exactly the same thing. So HA is transferred to DA, HB is transferred to DB. I am done. The data transfers are done. Once I execute this green statements, I have the configuration in the green box here. Then we will see how to do it. We will do the computation, okay? Then what we need to do is, we need to get the output back. So I have HC, which is empty. I didn't do anything on it, but I have DC, which is full now, okay? I did the kernel thing. I did the processing. So we will see how later, but assume that it is done. So I need to get it back. Again, the same destination, HC, source, DC, size, number of bytes that you want to transfer. But this time, instead of CUDA memcopy host to device, you just need to give CUDA memcopy device to host. And then you transfer the data from your GPU to the CPU. Then you free the locations that you, if you will not use them again, for this simple vector addition, you will not use them again. You free the memory that you allocated by saying like free in C, we have CUDA free in CUDA C, okay? CUDA free, the pointer name, CUDA free pointer name, CUDA free pointer name, and then we are done. Okay. Any questions about this pattern? So please type. In the meantime, I will go back here and I will talk about the memory a little bit and the kernel. So we will see how to write the kernels. But this picture show me that there is the host here, there is the GPU here, processing a kernel, running a kernel, which is a grid, okay? So I told you that you can have millions of threads performing as the same operation, running together, to perform a task on a GPU. And that set of threads is organized as a grid, which is a 3-dimensional structure. In this one, though, it is only 1-dimensional. So, sorry, let me see. Yeah, I mean, we have block 0, 0, block 1, 1. So grids, or a single grid, one kernel, one grid is doing it. It contains blocks. So it can be like this one here, 2 blocks. This is 1-dimensional. So this is block 0 and block 1. So forget about this thing. And then each block can also be 3-dimensional, but in this example, it is 1-dimensional. So we have thread 0 and thread 1 at each block, okay? So overall, this grid, for instance, this one, this very, very basic one, contains 2 blocks, each containing 2 threads. So overall, this grid contains 4 threads, executing the kernel, okay? They are reaching global memory while doing it, reading data, processing it, writing it back. So this thing is, and we have also registers, okay, for each core here, and registers are used again as they are used on the CPU. So the device code that the threads in the grid can do read, write per thread registers, so you can use them. You can say, for instance, integer I. So the value is stored in these registers. Use the global memory and the shared memory. We didn't see the shared memory, we will see it. And the host code can transfer data from per grid global memory. So we know now how to do that. So the host code can write things here, but not here. Device code can write things here, read things here, use shared memory, which host code cannot do. And many more also memory types will be later will come. But currently, you just need to know that what we will do for GPU processing is initiate a bunch of threads. And we will say that, okay, we will organize them in a grid. And we will say that, okay, do this. And whatever they do is really very simple. They will just use the registers, perform the computation, write the results back to global memory. Okay, so we already solved CUDA malloc. It allocates an object in the device global memory, 2 parameters, address of a pointer to the allocated object, size of allocated object in terms of bytes. This is input, this is output, okay? So the first parameter, you can consider that as an output because it is allocating some memory and putting the address on the first parameter. CUDA free frees object from device global memory, 1 parameter, which is input pointer to freed object. CUDA memcopy, memory data transfer, requires 4 parameters, pointer to this destination, pointer to source, number of bytes, and type direction of the transfer. Transfer to device is synchronous with respect to host, okay? So if you are doing CUDA memcopy, it is synchronous with respect to host. So host thread waits there, okay? It's not asynchronous, host thread doesn't continue. With kernels, we will see that the kernels are asynchronous, so they are non-blocking, the threads continue immediately. Okay, so you don't have any questions, so let's continue. We have, as I told you, there are ways to unify these 2 memories in a way that you only allocate one thing, okay? And the management, you only allocate one area, and the transfers, data transfers, management, etc., is done automatically, So in this one, for instance, we have 2 copies of the A. So we have 2 copies of A, one on the host, one on the device. Why? I mean, we can have a unified memory, A somewhere, and whenever we access it through the GPU, we can make the updates on the GPU and write it back to the host. So, and also we can do the same from the host. So that can be managed automatically. So there's a single, if you use CUDA malloc managed instead of CUDA malloc, the parameter setting is the same. I mean, the output, this guy, the address of the location that will be given to you, and this number of bytes. So it's a single memory space for all CPUs and GPUs, maintain single copy of the data, CUDA managed data. So this is on-demand page migration. Whenever you need the data, it will come to the GPU, okay? But page by page, you don't need to bring it at once. So page by page means that the host, all the data is divided into pages, and whenever you request something here, that page will come to the GPU, and you do some updates on that. Okay, you can do some updates on that. So these 2 things, this thing is compatible with CUDA malloc, CUDA free, and you can optimize the behavior, the management behavior behind the scenes by using CUDA mem advise and CUDA memcopy async. So, in short, again, unified memory is a single memory address space accessible from both host and from the device. The hardware and software handles automatically the data migration between the host and the device, maintaining consistency between them. So this is the same, but now we have the device code can read, write, manage memory, unified memory, and the host code can also have read, write, manage memory. So that these 2 are now possible compared to the previous one. So let's see how this works if you want to do vector addition. The same operation. Before, what we were doing, allocating device pointers, copying the data, getting the data back. Now the code, in fact, is really shortened. So we have MA, managed A this time, not H, not D, M, MB and MC, and CUDA malloc managed. So this is, I mean, you allocate, okay, you allocate it, and you perform the memory initialization on the host. So I mean, when I say memory initialization, I mean, you put the content inside A and B, okay, on the host by saying MA0 is equal to 0, MA0, MA1 is equal to 1, etc., etc. Then the kernel is executed, and then you free the values here with CUDA free this time, not free, actual simple free, but with CUDA free. And whenever the device tries to access these MA and NB content, the data will be brought to the device page by page. Okay, so that is done automatically. You don't need to do anything. So before, allocation on the device, transfer to the device, kernel execution, get the data back to the host, data output back to the host, free everything on the device. Now, allocate the memory, manage memory for both device, host and device. Memory initialization on the host. Before we were assuming memory data is coming from here, okay? Now, suppose that you initialize it here and execute the kernel, and after that, get the data back. Okay. So probably this will not be interesting for you because now we have CUDA 11, I mean, maybe 12, I don't know. So prior to compute capability 6.x, there is no specialized hardware units to improve unified memory efficiency. For data migration, the full memory block needs to be copied synchronically by the driver and no memory oversubscription. This is important. I mean, really important. Compute capability 6.x, there are specialized hardware units managing page faulting. So data is migrated on demand. So every access is page by page handled. If the data is not there, the corresponding page is brought to the device and it is handled. Not the full memory block is copied. And we have this possibility to oversubscribe memory, enabling larger arrays than the device memory size. So if you have a GTX 3090, and if you want to allocate 30 gigabytes of managed memory, now it is possible. Before it wasn't possible. Since you bring the data page by page, it doesn't matter, in fact. So you don't need to store the whole 30 gigabytes, 40 gigabytes on the GPU memory now at once, okay? Whenever you need some part, that page comes for you. Okay. So let's try to do one example. Okay. I will also put these along with the slides and the video links to the Indico webpage. So for the first two examples, I think we have, so let me, Okay, now I have this main.cc here. And if you open it, you see that there is nothing inside, okay? Okay, so how do we compile it? To learn it, let me try to see this. Yeah, to learn it, okay, we have MVCC. Okay, so if you, for instance, do this, it looks like I have CUDA 11.2, and then if you give the code to main.cc, if you give main.cc to MVCC, it compiles and it produces hello world. Okay, so we didn't see any kernel yet. Okay, so now we have that, and we want to have a dummy kernel, and we want to call it, and we want GPU does something for us because we learned data transfers, we learned unified memory, which is really powerful. Now the only part that we are missing for the first encounter with CUDA is the kernel, the actual computation part. So this is the let's go back to here, a couple of more slides, and after that we will go back to the application, the example. So let me skip this one. I will come to that. Okay, there is no kernel execution. So in GPUs, they are silent devices. They don't complain too much. So tomorrow you will see advanced debugging and profiling. But at least you can do this, okay? So you can have the return value of CUDA malloc, for instance, with this as this type, CUDA error T, and check if it is CUDA success. If everything goes well, you will see that this is CUDA success. Otherwise, you can decode the error code, CUDA error T object, by using the function CUDA get error string, and after that, see what's happening, what's the problem with your computation. So that is the basic thing that you need to do, especially for the beginning. You need to check the return value of every CUDA malloc and every function call that you have, okay? Every kernel execution. There are advanced things, commands, tools, which you will probably see tomorrow. I will also do some examples of them today, but the main content will be tomorrow about them. So to learn about CUDA threads, the main mechanism for exploiting of data parallelism, this is the next objective. Hierarchical thread organization, we will understand that. Launching parallel execution, we will learn that. Thread index to data index mapping, and we will learn that. Okay, so we will perform vector addition again. And in the CUDA execution model, we have heterogeneous host, device, GPU, application, C program, which means that we have the CPU code and the GPU code in the same file, maybe, okay? So how does the GPU understands, how does the compiler, understands which parts to compile it for which device, which codes will be executed on which device, or CPU or GPU, etc., etc. So we need, compiler must understand it, right? But they will work like this at the end. So we will learn how to do that, but they will work like this. So the first, the serial code, or maybe the OpenMP parallel code will be executed here by the host. Then some part of the computation will be offloaded to the kernel, so GPU, by executing a kernel. So you probably, realize that I am using kernel for GPU functions. This is just the common terminology again. Again, some serial code, maybe OpenMP code, parallel code here. And after that, another parallel kernel, which will be executed on the device. So we will see what these things mean. But simply, this is the function name, kernel name that you call. This is the number of blocks in your grid. In fact, as I told you, grid is a 3-dimensional structure. And if you have a single number here, grid is a 1-dimensional structure. What does it mean? The 3-dimensional structure becomes 1-dimensional structure. It just means that the other dimensions are 1. So you can either say, for instance, I have 30 times 5 times 5 blocks in my grid. So 25 times 30, 750 blocks in my grid, something like that. Or you can say 30 times 1 times 1 blocks in my grid, or just say 30. Okay, so this, you can put a single number here, or a struct, special struct, where you specify each dimensions. And the same analogy goes from block to thread. So grid to block, the same. I told you that how can you specify the dimensions of your grid, and the dimensions of your block is specified by NTID here. If you have a 1-dimensional grid with 1-dimensional blocks, then you just need to put here the number of blocks that you want to execute, the number of threads that you want to execute, and you're done. Okay. Which will be the case for vector addition, because vector is a 1-dimensional structure anyways. Why we need to extend this to multi-dimensional thread organization, which can be useful for tensors, images, 3D, volumetric data, but for 1-dimensional data, use only numbers, simple numbers. So a program is a set of instructions stored in memory that can be read, interpreted, and executed by the hardware. Both CPUs and GPUs are designed based on different instruction sets. Program instructions operate on data stored in memory and on registers. We already saw these things. And this is a thread as a von Neumann processor thing. So this is the processing unit, this is the memory, this is the control, and this is the IO. You already know this architecture from the basic pictures that we saw. And what the GPU course will do is similar to this one, in fact, but there will be a little bit difference for the SIMT part of it. So we will see how it will change. Okay, a CUDA kernel is executed by a grid, which is an array, it says, but it's a three-dimensional data, as I told you. Threads. All threads in a grid run the same kernel code. Single program, multiple data. Paradigm is happening here. Each thread has indexes that it uses to compute memory addresses and make control decisions. So the vector addition code, the for loop that we saw before, for I is from 0 to n, I plus plus, Ci is equal to AI plus Bi, that code becomes this. So if you initiate n threads, if you initiate one thread per pair of elements that you add, you first will find your global thread ID, which will be used to access the data items and the output location that you need, and you perform this thing. So this is your kernel. As you see, there is no loop here. Each thread executes that thing. You initiate n threads. We will come to these parameters, but the first thread will have ID 0. The last thread will have, if the vector size is 256, the last thread will have I is equal to 255, and every operation will be performed here. Every operation required, every operation that you perform in a usual traditional vector addition code will also be performed here. But that will be your code, that will be your kernel, okay? So let me talk about this briefly. Block IDX, block DIMX, and thread IDX. So since we are dealing with vectors, as I told you, grid is a one-dimensional structure. So each block has a single ID that is coming from block IDX-X. If grid is two-dimensional, then block IDX-Y will have other values than 1. But since we have a single-dimensional grid, block, this is, I can say that this is block 0, this is block 1, this is block 2, this is block 3, right? So I need a single number to specify each block, to identify each block. And that block IDX-X is that number, okay? The X coordinate of the block on that grid hierarchy, which is one-dimensional, so I only need that. Block DIMX, I told you that blocks are also one-dimensional, and the other sizes are 1. So that block has maybe 8 threads inside, maybe 32 threads inside, okay? When I multiply the ID of the block with the number of threads inside the block, I find the ID of the first thread inside that block, global ID of the first thread inside that block. We will have a figure about it. And thread IDX-X is the local ID of the thread inside the block. Again, I need a single number because blocks are one-dimensional. So this will give me the global ID of the thread, okay? So let's visualize better. Thread block 0, thread block 1, thread block n-1. Suppose that you have 256 times n elements in your vectors. So I am initializing 256 times n threads, which are organized in n blocks, and the block dimension is 256, okay? So the thread IDX-X for the first thread here is 0. Again, the thread IDX-X for the first thread is 0. Again, the thread IDX-X for the first thread in this block, in block n-1, is also 0. But this thing here, so let's do this operation. So block IDX-X, this is 0 for this block, 1 for this block, n-1 for this block. Suppose that we are performing that thing here. 1 times 256 plus thread ID. So this guy will have 256 plus 2, right? So it is 258. and it will know that he will process vector elements 258. So A258 plus B258 is equal to C258, okay? So this is how you map your threads to the data. This is how you map your threads to the computation. So divide thread array into multiple blocks, the whole grid into multiple blocks. Threads within a block cooperate with shared memory, atomic operations, and barrier synchronization. You can ignore this for now. We will see shared memory. And threads in different blocks do not interact. So that's important. So within a block, you can communicate. If you are thread this guy and this guy, we will see that they share a shared memory, so they can write, read from the shared memory, okay? But the threads in different blocks, they do not interact. They can interact via global memory, okay? So that's the only way. There are block-wise synchronization mechanisms already implemented. So you can say sync threads and all the threads come to that barrier, okay? But we don't have such a mechanism for the device level. So with different blocks, you need to implement it manually. So block IDX and thread IDX. So this is one picture that summarizes the things. So block IDX, it can be one-dimensional, two-dimensional, or three-dimensional. Thread IDX, again, one-dimensional, two-dimensional, three-dimensional. In fact, I mean, every time it is three-dimensional, but the dimensions are one, as I told you. So here, for instance, let's see. I have a two-dimensional grid. So I have block 0, 0, block 0, 1, block 1, 0, block 1, 1. So 4 blocks organized in a two-dimensional way. And each block here is a three-dimensional block. Okay? Which means that the threads are organized in a three-dimensional way. So there are 8 threads inside each block, which is organized in, let me see, this is in fact, no, this, oh, sorry, there are 16 threads inside each block, my bad. It's my bad, sorry. In organized in, okay, so this makes more sense. So 4 by 2 by 2 manner, okay? So this kind of organization can simplify memory addressing when processing multidimensional data, like image processing data or solving PDEs on volumes. So this is the block IDX and grid IDX thing. So this is the first example. So let's do this, in fact. So let's go back to here. And we will continue with the example again here. Dışarıda bırakırım ya. Sorry, guys. Okay, let me copy this one to here. Let me open this one. So as you see, I have a kernel here, which does nothing. So that's a dummy kernel, very, very dummy kernel. I just write its name here, and then I put these 3 things here, and there's these 3 things here. That's the syntax that we saw, number of blocks and number of threads. And after that, they say printf. Well, I mean, it says nothing, in fact. From the GPU, it says this from the CPU. Okay, so let me compile it. It's compiled, and I saw hello world, and that's all, right? Okay, so let me try this. Let me put this here. I don't see anything. Because I told you that this is non-blocking. So this is asynchronous code. So the CPU thread comes here, offloads this to the GPU, and after that, it continues, it returns. I mean, there is no time for me to see the output from the GPU. So there is something called CUDA device synchronize. And once you write this here, now the CPU thread will wait there. Okay, so the CPU thread will wait here. Okay, until all the things that you send to the device are completed. And when you execute that again, this time you see the hello world. And we executed one block, which contains one thread. So let's execute one block, which contains 32 threads. Now I see 32 times hello world. And I don't change the kernel as you see. So this thing is executed by all the threads. Don't forget, all the threads inside your grid. Okay, we didn't do the data block IDX thread IDX part, but we will have example for that in the next part of the course. But for instance, you can increase the number of blocks. Okay. And as you see, we have now 64 of them. So we can have more information, right? So we can have thread IDX X, maybe block ID. It's specified with this. Block IDX X, thread IDX X. Let's see. So this hello world is coming from the first block, the 17th thread of the second block. Okay, and this is coming from the first thread of the first block. Okay, so as you see, in fact, there is no ordering among the blocks. So the block 2 executed first and block 1 executed later. So you can have, in fact, I mean, maybe to find the global ID, what were we doing? So block IDX X is my block ID. My block ID, I'm a thread, and this is the ID of my block. I multiply it with the number of threads inside my block, sorry, inside every block, in fact. And then I add my local thread ID here. And then I compile. And it doesn't print because of this. Okay, let's see what we have. As you see, these numbers, the third number here is going from 0 to 63 because I have 64 threads at them. Okay. Could you explain a little more the multidimensional thread part? Yes, but this is 1 p.m. So let's continue this for the at the beginning. Let's continue this at the beginning of the second lecture. Thanks, and let's meet at 2. Yes, the records will be available for viewing later.